Hi, welcome to my video. Now in this video, we are going to discuss gas laws. Now, there are four laws that were studied under the gas laws. We have Boyle's law, we have the Charles's law, we have Gay-Lussac's law, and we have the Avogadro's law. But in this module, which is physical chemistry, we are only going to focus only on three laws, which is Boyle's law, Charles's law, and the Avogadro's law. Okay? All right. So now, to make things much more easier, this is what I love saying to people when I explain this module, when I explain this concept. We have three states of matter, right? We have gas, we have liquid, and we have the solids. But now we are only focusing on the gases. We all know different types of gases. We can talk about the methane gas. We can talk about a hydrogen gas. We can talk about the nitrogen gas. Think of anything that says gas. Assume that you know what is gas. Okay? That's just how it works so that everything can make sense. Now let us start. So now what you see here on the board, these are four, we call these four basic variables. These are four basic variables of gases. Now, these four basic variables of gases, they were studied by these scientists who postulated all of these laws. Now, these variables, they are very important in gas laws. But now I will tell you how these variables were studied. In the laboratory, these scientists, what they did is they considered only two variables, okay? They considered only two variables to be studied. Like, for example, say this scientist decided to choose volume and temperature. So when he chose these two variables, he wanted to see the relationship between these two variables in regards to gases when these other two variables were kept constant. These variables are always there when it comes to gases, meaning we say that all gas under moderate conditions, they behave simple with respect to these variables, okay? So that means any gaseous molecule or any gaseous compound will have an experience of these four variables that you see here on the board. So now these scientists, when they wanted to postulate their laws, like I said, they took these variables and studied them. For an example, if let's say, for an example, this scientist wanted to know the relationship between the volume and the temperature of a gas, that when I change the temperature of these gaseous molecules, what is going to happen with the volume? I'm going to measure it. You understand what I'm saying? So meaning if two variables were chosen to be studied, that means the other remaining variables will be kept constant, okay? But like I said, there are many different types of gases laws, the one that I have just mentioned. That means other scientists will be like, no, I saw this scientist studied volume and the temperature. What if maybe I want to study volume and the pressure? And therefore, this other scientist, he came along and then he took volume and the pressure. He wanted to see the relationship between these two variables of a gaseous molecule. And then he kept these other remaining variables constant. And all of these scientists, they managed to do what? To postulate their laws based on their studies. Okay? All right. So now, all of these laws of scientists, okay, we have the equations. You will see there are equations that are going to result by the end of each law that, according to this scientist, this is how the equation actually explains the law. Okay, we're going to explain the law using words. We're going to explain the law using the equation. Now, all of these equations together at the end of this, towards the end of this concept. That means we're going to combine all of these equations to form what you call the ideal gas equation law. Okay? All right. So I hope what I have just explained, it does make sense. Now, let us start with the first law of our very own scientist. Now, the first law here, it is called the Boyle's law, which was postulated by Robert Boyle in 1660. Now, Boyle, after his findings or after his experiment of gases, this is what he said, this is what he concluded. He said that the volume of a fixed quantity of a gas is inversely proportional to the pressure, so long as the temperature remains constant. Now, this scientist, he spoke about 4 basic variables. Let us start there. He spoke about the volume, he spoke about the quantity of a gas, he spoke about the pressure, he also spoke about the temperature. These are 4 basic variables of gases. But now, you want to understand that this scientist, which 2 variables were kept constant and which 2 variables were studied. According to this scientist, which is Boyle, Robert Boyle, he said that I am going to keep the quantity of a gas constant, meaning the number of moles of a gas constant. Now, let's talk about the constant variables, okay? The constant variables in this case were number of moles and the temperature, because he kept quantity of gases fixed, meaning they were constant, and the temperature remained the same. But this scientist who's Boyle, Robert Boyle, he said, I want to determine the relationship now between these 2 variables, between the volume and the pressure. This is what he wanted to determine, right? Right. Now, according to this scientist, his conclusion was when volume and the pressure changes, while the number of moles of gas and the temperature remains the same, the volume will be inversely proportional to the pressure. Oh, that means the volume will be inversely proportional to pressure. That means the volume will be inversely proportional to pressure, not direct. This is direct proportion. But if you want to use the direct proportion sign, you need to use the inverse of our pressure. Okay? He said, oh, that means when volume increases, the pressure will decrease. It's vice versa. I will make a practical example so that you can see what do we mean when we say that, okay? Now, this is what he did, okay? This scientist, okay? Let's start with a practical example. Practical example. Now, Boyle, he went in the lab, right? He went in the lab to study what? To study the behavior of gases based on this condition, based on these variables, okay? So now say, for an example, here we have a beaker, and this beaker has a compressor, okay? Okay, it has a compressor, right? And therefore here, we have the molecules of gas, which is being studied. Now here, it is the very same beaker, but you have to understand that it is a transformation from there to here. Okay, but I'll explain that. Let me not use this. I have to, let me just, okay. So let me just do this. Okay. So this is also the very same thing. And then here we have the gaseous molecules. Now this is what is happening. Boyle, he simply did this practical thing, which is easy, okay? In beaker A, also in beaker B, these are the same, just it's a transformation from here to there, okay? Now, in this beaker, the volume of gas, it is most definitely high, right? The pressure of these gaseous molecules, it is most definitely low. What do I mean when I say that? Now, the gaseous molecules in this container, they occupy a large volume in this container, as we know that the gases, they move freely in its container. So in this container, the volume of these gases is high, right? And then what about the pressure of these gaseous molecules in this container? It's low, meaning these gaseous molecules, they are not under high pressure, they are not compressed, they move freely, meaning they are not under high pressure, they are not experiencing any pressure, they are not pressurized because they can move freely in this container. But now say we take our compressor and then we compress this gaseous molecule to result into something that looks like this. Now, this is what is happening. For a fact that we decreased the volume occupied by these gaseous molecules, that means we can simply say the volume occupied by these gaseous molecules has decreased. And therefore, what is happening with the pressure of these molecules as we decrease the volume? The pressure will most definitely increase. That means these molecules, they experience high pressure because they are compressed. They are pegged closely to one another. They can't move that freely as much they're supposed to move. So that means these gaseous molecules, they are under high pressure. They experience a high pressure because the volume now it is low because of a compression. Now, this is what I want you to understand. The amount of gases were kept constant since when we had our compressor, which seals the whole beaker. That means there are no gaseous molecules that are exiting out of the system, number one. Number two, the temperature was kept constant, okay? Meaning there was no increase in temperature, there was nothing at all. So that means these two variables, which is amount of gas in number of moles and temperature, were kept constant by Boyle when he was running this experiment. And therefore, when he decreased the volume by compressing the gaseous molecules from his gauge pressure, he read that the pressure decreased. That means the higher the volume, he had his gauge pressure there, he measured the pressure was low. These gaseous molecules were experiencing low pressure. But when he decreased, when he lowered the compressor in a beaker by decreasing the volume of the gaseous molecules, and therefore these gaseous molecules, they experienced high pressure, they were under high pressure, okay? So that means he then concluded that when the volume of a fixed quantity of gas is inversely proportional to the pressure so as the temperature remains constant. This is basically what Boyle came into conclusion. He came into conclusion based on this simple thing, which I believe everything does make sense when you think of it. Okay? So now, this is explained. He explained this in words. This is an explanation of Boyle's law in words, and this is the explanation of Boyle's law practically. We can also explain this graphically, but how? Let me show you how, okay? So graphical example of this law, or e.g., you can just write example, graphic, it's fine, I'll just say graphic. Graphic example of this law is that we know that graphically, we have this, okay? So here we have volume, and then here we have pressure, and therefore here we have a steady degrees, exponential degrees. Sorry about that. We have exponential degrees of, let me fix my graph. It doesn't look okay, it doesn't look nice. So here we're gonna have our graph. Let me just, all right. So now here we have the relationship. It's an experiment that shows the relationship between volume and the pressure. But you have to understand that it is not the direct proportion, okay? So now this is what is happening. So when the volume decreases, what is happening with the pressure? The pressure increases, since well we know that these two variables are inversely proportional. When the variables are inversely proportional, means the other one, when it goes down, the other one goes up. They oppose each other, okay? So now this graphical can also be presented in this way, the relationship between them using a linear function, okay? So here we can have V, and then here we have 1 over P, which is the direct proportion. But you want to understand how this direct proportion was brought up now. Now, let me show you how. So now we're going to use the equation. According to this, we saw that the volume, it is directly proportional to the inverse of pressure, which is 2, okay? But now, how? Now, say this is the inverse proportion. So we're going to introduce the constant. So remember, the constant we had, we're going to multiply this thing by the constant, and then we include the equation, the equal sign. The constant we had in this case was what? Was number of moles and the temperature. Okay, was number of moles and the temperature. So meaning the number of moles and temperature were kept constant, and the value of R in this case were kept constant. Okay, so meaning this is the equation that we can use, whereby this constant, it will represent the gradient of this equation, and we know that the gradient is everything constant. That means the temperature, the number of moles, everything that was kept constant will represent the slope of this graph. And in this case, 1 over P, it is our variable that we are going to write it on our x-axis, and therefore V in this case, it is our variable, which is volume, that will be writing in our y-axis, and therefore C, which is the temperature, the slope of this graph under Boyle's law, the slope of this graph, it represents what? It represents everything constant, such as number of moles and temperature. Okay, so this is how Boyle actually explained his law. Do you all understand what I'm saying? So now this is what is happening. We know that we have the ideal gas equation, okay? But I don't want to talk about it right now. I want to talk about it at the end of this session. Okay. The thing is, we know that it is denoted by PV is equals to nRT. So now what you see over here, if I want to make my V subject to the formula, I'm going to have to divide both sides by P, whereby I'm going to have nRT divided by P. And therefore, remember, in Boyle's law, we have to keep this constant. Already R is our constant, N and T are kept constant. I'll just write C. And therefore, we're going to have V, which is equal to C over P, which is the same as V is equal to C multiplied by 1 over P, which is what I have just explained to you over there from the ideal gas equation. Okay, I hope that it is making sense. Now, let's talk about Charles's law, okay? Shall we check? That's how they say his name, as French say. So now we call him Charles. So now here we have Charles's law. Charles's law is one of the laws, again, of gases that was postulated by himself, Mr. Charles, in 1780s after Boyle's law. He was like, oh, I see, my brother, what you did over there. I can also do the very same thing, but now using different variables instead of the ones that you did, because I wouldn't come here to postulate the law based on what you have already discovered. Let me do something different then, okay? So now, this law states that the volume of a fixed amount of gas is directly proportional to its temperature so long pressure remains constant. Okay, again here we still have 4 of them. Okay, the volume, okay, it's fixed. Amount of gas, I wanted to highlight amount of gas, the temperature and the pressure. So now this is what is happening. According to this guy over here, the variables that he wanted to keep constant are as follows. Constant variables where he kept again number of moles constant as Boyle did. So he took number of moles of gases, the number of moles, the number of constant, the number of this thingy of amount of gas constant by not escaping, again because this gas can escape, remember that, by not escaping or by not adding extra more molecules of gas in a system. And again, another variable that he decided to keep constant in this experiment, so long pressure remains constant, and the pressure, which is P, right? And therefore, what he studied was volume and temperature. Okay, remember Boyle, he studied volume and pressure, but Charles, he studied volume and temperature. Okay, so he wanted to determine the relationship between volume and temperature. Okay, this is what he wanted to study. So now Charles said that, oh, okay, if maybe I keep these two constant, the number of moles of a gas and its pressure constant, and therefore I change the volumes or the temperature of this experiment, what is going to happen with one variable? If I change the volume, what's going to happen with temperature? If I change the temperature, what's going to happen with the volume while I keep these two variables constant? Now he realized that when he keep these two variables constant and changing these two variables constant, he realized that the volume of that fixed amount, it will be fixed amount of gas, it will be directly proportional to its temperature, and while the pressure is constant. So that means he realized that the volume is now directly proportional to temperature, not inversely proportional like Charles, like Boyle. So he said that, oh, that means the volume will be exactly directly proportional to what? Will be exactly directly proportional to temperature. That's what he realized. Okay, meaning when the volume increases, the temperature increases, which does make sense, but I'll show you how. Okay, now let us do again a practical example. Okay, say we have a practical example. Now in this practical example, I am going to use the balloons. Okay, I'm going to use the balloon. So now a transformation of a balloon. So say here we have a balloon. Okay, I'm not good at drawing, I know that. And therefore this a balloon over here, it is expanded now. Okay, so now let's have a look at this balloon. I'll call this A, I'll call this B, but do not forget, this is also a transformation. It is the same thing, but under different conditions. Okay, so now what you see over here, the balloon is most definitely sealed. So that means the gas that is found in these two balloons, it is the same. And number two, the amount of gas that is found in this balloon, again, it is most definitely same. And the pressure, it is most definitely kept constant, okay? But now this is what is happening. Now, say for an example, in this balloon, we put this balloon during the night. It's then during the night, okay? During the night, it's cold. Let's assume that during the night it's cold. So here it experiences coldness. And therefore here it's during the day, whereby we, during the day we can say warm or hot. I'll choose hot, whereby it's hot, okay? So now we expose this balloon at different conditions. And these different conditions are solely based on the temperature. So that means during the day, we know that the temperature is low. During the night, we know that the temperature is low because it is cold. And then during the day, we know that it's hot and the temperature, it is high. It is high, right? Now, again, during the night, whereby it is cold, whereby we're going to experience lower temperatures. Now, what is going to happen with the volume occupied by these gaseous molecules? The volume, it is most definitely low, again, compared to that. But now when we take the very same balloon during the day, whereby the temperatures are now high, this balloon will most definitely raise. Then during the day, we know that the temperature is high, and therefore this temperature will heat up these gaseous molecules to move vigorously in this balloon. And this as these molecules move vigorously in this balloon, what is going to happen? The balloon will expand, okay? The balloon will expand, whereby the volume occupied by these gaseous molecules will be high. Therefore, in this case, we can see that when the temperature increases, the volume does also increases. Okay, under low temperature, we have low volume. Under high temperature, we have high volume. That's just how it works. So this is just a practical example that explains this guy's law, who is Charles, which is the Charles law, who says when the volume of a fixed amount of gas is directly proportional to its temperature, so long pressure remains constant. This is what he was explaining over here. Okay, and then graphically we can explain this. Graphically, we have graphical example. We have the y-axis, we have the x-axis, and then here we have our volume, and then here we have our pressure. Okay, sorry, not pressure, temperature. Here we have our temperature, and therefore because they are directly proportional, so that means you're going to have a linear function as it is. So that means when volume increases, pressure does also, not pressure, temperature does also increases. Okay, all right. So now again, to explain this law using the equation, to explain this law once more again using the equation, remember these were kept constant. So that means V will be equals to how much? Will be equals to our constant multiplied by our temperature. Do not forget these constants are what? Are these two, okay? Therefore, we have a linear function. This is a linear function. So this, it is the gradient of our linear function, which is constant. Okay, again, from the ideal gas law, we know that the PV is equals to nRT. So in this case, we're going to make V subject to the formula. So that means V is going to be equals to nR divided by V multiplied by the very same temperature, just divided both sides by V. But remember, this supposed to be kept constant. So that means we're going to have V is equals to constant multiplied by temperature, which is the very same equation that I have just showed you over here, without using the ideal gas equation. Okay, this is how this experiment actually works of Charles's law. I hope everything is making sense. Right, so now here we have Avogadro's law by Amedeo Avogadro, who came after Charles's law was postulated. He also postulated his law. Now, Avogadro, he said that he stated his law as the volume of a gas at a constant temperature and the pressure is directly proportional to the number of moles of volume of the gas. Now, what you see here over here, again, let us talk about the variables, 4 basic variables: the volume of a gas, the temperature, right? The pressure, and the amount of moles. These are 4 basic variables in this law of Avogadro. So now what was kept constant? Constant variables. Now what was kept constant? Let's have a look. the temperature was kept constant and the pressure was kept constant, okay? The temperature and the pressure were kept constant. So now we wanted to determine the relationship between what? Avogadro wanted to determine the relationship between the volume and the number of moles of a gas, okay? And then he also found the direct proportion. But how? Now let's talk about this once more again. Avogadro said that when the volume of a gas at a constant temperature and pressure, the volume of that gas will be directly proportional to the number of moles of the gas, meaning the volume will be directly proportional to the what? To the number of moles of that gas. Remember, for everything to make sense, let us start by doing the practical example, okay? Practical example, e.g., okay? Now, in this practical example, say for instance, you have a beaker, okay? You have a beaker. I'm sorry about that. You have a beaker, and then you have a transformation of a beaker, of what is happening inside of the beaker. Here we have this. Can we start here? And then there you have that. In fact, now this is what I want to do, okay? I want to use here, I want to use different beakers, okay? Here I'm going to use different beakers, not a transformation. I have beaker A and then I have beaker B. And then here, say I have gaseous molecules, and also there I have gaseous molecules, right? So now, in this beaker, we have, you can see the beaker is the same, okay? The beaker is the same. The temperature experienced by these gaseous molecules in these different beakers is the same. The pressure is the same. They are under they're under same pressure. If the pressure here it's whatever Pascal, here the pressure is going to be the very same pressure. Because the thing is, here we have many molecules, and then here we have fewer molecules. So that's why we can manage the pressure experienced by these two beakers, okay? So the pressure here is the same as that one, okay? So now here, our volume is V, and then here, our volume is twice, okay? Why am I saying that? Because now, this is what is happening. The number of moles here, I mean, like, you can't take this number of moles and want to put this number of moles in this lower volume. How is this going to fit in? It is not going to fit in. It's not going to be able to fit in. So that means double number of moles of this. So here we just have N. So here we have number of moles, but if we want to double this number of moles, we have to change our volume. We have to change our beaker, because this beaker can occupy the exact number of moles in this beaker. Meaning, say for an example, okay? Say for an example, this beaker can occupy, I'm just making an example, 10 moles of what? Of gaseous molecules. Why? Because the beaker has a volume of, say, 20 liters. I'm just making an example, 20 liters, okay? Now, here's the thing. If we double our number of moles to be 20 moles, will 20 mole fit in the beaker of a volume of 20 liters? No, this beaker, it can only take a maximum of 10 moles. So that means if we want to insert 20 moles of gaseous molecules in a beaker, we're supposed to use a beaker that is double the size of this beaker, which is most definitely 40 liters. So now in this case, we can see that when we increase the number of moles, we're supposed to increase the volume. Because if we have higher number of moles and we have lower volume, this higher number of moles won't be able to fit inside. You understand? And do not forget, temperature is supposed to be kept constant so that we don't have the motion of what? We don't have that vigorous motion of the gaseous molecules, and the pressure is supposed to be kept constant. Okay, so now in this case, this is a practical example of Avogadro's law. Now graphically, we can example graphically say we have our Cartesian plane in y-axis and x-axis. So here we have v, and then here we have number of moles, and therefore these variables, they are directly proportional to one another, meaning when volume increases, the number of moles supposed to increase as well. Okay, and therefore remember this is a linear function. To formulate the equation, so remember we're gonna say v is equals to constant multiplied by number of moles. But do not forget, what is this constant? Constant is a combination of temperature and pressure and other things that's supposed to be kept constant. So now the linear function, this linear function, its gradient will be presented by P's, the temperatures, the pressures, and all of that. From the ideal gas equation, PV is equals to nRT. So I want to make volume subject of the formula. That means I'm going to have to divide both sides by P. So that means I'm going to have nRT divide by what? Divide by P. So that means this will be our constant, and therefore you're going to have V is equals to this constant over here multiplied by N, and therefore this is the same as this formula over there. So this is just a simple explanation on these laws that were postulated by these scientists, and I hope everything it is making sense.